It is crucial to understand geomagnetic storms because they impact navigation and communication systems. Their significance reaches beyond space science and observations, influencing technology, commerce, and everyday life. The occurrence of geomagnetic storms takes place in different ways. First is through the impact of solar wind particles. Based on solar energy inputs, geomagnetic storms occur through the corpuscular radiation from the sun. Solar corpuscular radiation consists of solar wind, which contains particles projected from the sun towards the Earth, guided by the interplanetary magnetic field. When the solar wind reaches speeds exceeding 500 kilometers per second, it is termed high-speed solar wind. The high-speed solar wind can cause geomagnetic storms upon impact. How does solar wind spark a geomagnetic storm? When the sun releases high-speed solar wind, particularly solar wind traveling towards the Earth at rates above 500 kilometers per second or much more, sometimes up to 800 kilometers per second, this gust of solar wind pressure compresses the magnetosphere initially. Especially with excessively fast solar winds, the outer magnetosphere becomes excessively disturbed, creating a complex oscillation of the magnetic field and the entire magnetospheric plasma. This phenomenon induces electric currents in the near-Earth space environment, which subsequently produce additional magnetic field variations. Collectively, these effects are referred to as a geomagnetic storm. Another cause of geomagnetic storms is coronal mass ejections, or CMEs. CMEs are dense clouds of particles from solar eruptions. Coronal mass ejections are releases of plasma and magnetic field from the sun's corona. They can expel billions of tons of coronal material and carry an embedded magnetic field that is stronger than the background solar wind interplanetary magnetic field strength. They appear to travel slower than solar winds due to their late arrival to Earth, taking between 1 to 4 or sometimes up to 5 days to reach Earth. The late arrival results from the time drag of the plasma cloud in space. A disturbance in the magnetosphere caused by a coronal mass ejection, or CME, creates a current that impacts the near-Earth space environment and generates a corresponding magnetic field. The intensity of a geomagnetic storm from a CME depends on the strength and direction of the interplanetary magnetic field, or IMF, starting with the shock arrival and lasting through the plasma cloud passage. Strong and south-directed CME-enhanced IMF leads to more intense storms. Coronal mass ejections frequently display different magnetic field directions as they pass, although some maintain a consistent direction. Typically, the impact of a CME on Earth's magnetosphere will promote the generation of geomagnetic storms. Geomagnetic storms can also result from magnetospheric charged particles entering through a direct magnetic connection between the Sun and Earth. When this rare link occurs, charged particles follow magnetic field lines into the magnetosphere, generating currents and causing variations in the magnetic field. When the interplanetary magnetic field and Earth's geomagnetic field lines are perpendicular, they undergo a process known as magnetic reconnection at the day-side magnetopause, which faces the Sun. During this event, plasma can penetrate through the magnetopause, allowing particles to pass through funnel-like regions called cusps, located over the Earth's north and south poles. In the outermost areas of each cusp, the plasma is drawn into the magnetic field lines and travels toward lower altitudes along those lines. As these particles accumulate in the Earth's magnetotail, it becomes increasingly stretched, marking the initial phase of a magnetic storm. Also, solar wind-stream interaction regions, or SIRs, and corrotating interaction regions, or CIRs, can cause geomagnetic storms and change the energetic particle environment and ionospheric composition on Earth. Corrotating interaction regions are recurring solar wind structures with velocity jumps and magnetic field compression. They form from the interaction between slow and fast solar wind streams originating from coronal holes. A corrotating interaction region occurs due to the interplay of wind flows with varying velocities. This phenomenon results from the solar rotation, which eventually causes the collision between these differing speed flows, forming a spiral pattern in the solar wind. When stream interaction regions, or SIRs, and corrotating interaction regions, known as CIRs, hit Earth's magnetic field, they can cause geomagnetic storms that affect spacecraft and technology. These interactions are crucial for space weather forecasting due to their impact on the magnetosphere and ionospheric composition. Geomagnetic storms affect our daily lives in different ways. Geomagnetic storms heat and distort the ionosphere, making long-range radio communication and GPS unreliable or ineffective. Increased solar wind during storms causes ionospheric expansion, which raises satellite drag and complicates orbit control. During geomagnetic storms, satellite electronics may sustain damage due to the accumulation and discharge of static electric charges. Additionally, astronauts and high-altitude pilots may experience elevated levels of radiation exposure. Induced currents in space cause rapid geomagnetic field changes. The induced currents can lead to voltage spikes in power grids and potential blackouts on Earth. The awareness of geomagnetic storms is important, considering its effects on our daily life. We are thankful for the abundant educational materials from different articles and sources from different bodies such as NASA, NOAA, European Space Agency, ESA, U.S. Geological Survey, and other scientific research and educators. To encourage us in producing more content like this, please subscribe to our channel, like and share the videos with your friends, and click the notification bell for latest uploads.